instruments, you can read about how the instrument works in your book. And you'll hear about that in lecture. But I want to stick to how to solve problems, which is what you're going to need to do NMR anyway. So NMR spectroscopy, there's different types. You take different nuclei of atoms, that's where nuclear comes from, and they resonate. That means they spin flip if you put them inside of a really strong magnet and you put radio frequency waves, the lowest energy waves. If you put protons, now protons are nuclei, for instance, protons are H1, only one proton in the nucleus, that's it. If you put nuclei in a sample, let's say I just had a sack of hydrogens. Those nuclei we learned have spin values of 1. And so they have a spin to them. And so if I just have a sack of protons, those protons in a non-magnetic environment are just going to spin in all different directions. They're going to cancel each other out. That magnetic moment or that spin, it just goes all different ways. These are magnetic moments, little mini magnets. When you are in physics, you will learn that when charge, like a cation or an anion, spins about an axis, it forms a magnetic moment, like a north-south magnet, a mini magnet in the opposite direction. Some of you've probably seen where you can take a copper wire and hook it up to a battery, and if you spin the copper wire around a spool, you can make a magnet. It's the same thing. But it's just charge and magnetism are orthogonal versions of the same thing. So when protons spin, they make mini magnets, but in a sample, the magnets are so weak that they just recess in all these different directions. But if you put those protons inside of a huge magnet called an NMR spectrometer. So here's a hollowed out magnet. There's a hole here. And we're going to put our sample down in there. And it's a whole bunch of protons. And this magnet inside of it is so strong that the protons either spin a line with the magnet. So here's our external magnet, or against the magnet. Okay. And these are called alpha beta spin states. So what happens is that the mini magnets they have a 50% chance of aligning with the big magnet, which we call BO, not like the odor, or they can align against it. But if you take radio frequency of a radio, seconds minus 1, so like the radio waves, and you shine or emit or pulse radio waves into your sample, some of the protons will absorb that radio radiation and they will spin flip. And when they spin flip, this is called resonance. And so we have nuclear magnetic resonance. The nuclei of an atom, any atom that has an overall spin, like a proton, when you put it in a magnet and you shine radio frequency on it, sometimes we call this RF, radio frequency, it will spin, flip, or resonate. And we can track that as an absorbance. And so this is another absorbance scale. So it's a spectroscopy. Now, when we spin absorb, we look at the spectrum. This is an NMR spectrum. And NMRs are weird because we only mark the x-axis. So the x-axis is called the chemical shift. And I won't get into the long story short, but it's not frequency. We convert frequency to chemical shift, which looks like this small delta symbol. Like here's a big delta symbol change. This is a small delta symbol, kind of like a partial negative or partial positive. That is the chemical shift symbol. And it's in parts per million, ppm. And the x-axis of a proton NMR, so we're looking at H1 NMR, protons in a sample. We choose protons because there's a lot of them, and organic molecules always have hydrogens. So we can always get an NMR of it. If we chose bromine, we couldn't do NMR on all of our samples, or phosphorus or something. So we choose a proton NMR, and the axis goes from 0 ppm all the way to window, usually going to 12 ppm. So if you look at your x-axis and it gets bigger as you go left to right, from 0 to 12, you're looking at a proton NMR. Now, when we go left to right, we have different types of hydrogens. Hydrogens are not just naked hydrogens, like I said before, like a sack of hydrogens. They are bonded to carbons, they are bonded to oxygens, they are bonded to other things like nitrogen, all right? And this changes their chemical environment. And as it turns out, When hydrogens are electron rich, so they're around non-electronegative atoms, they absorb down or upfield. This is called upfield, the right-hand side, where you're near zero. So a standard alkane hydrogen, because hydrocarbons of alkanes are electron rich, there's no electronegative atoms, alkane hydrogens will usually absorb about 1 ppm. Okay? Now, as the hydrogen is attached to more electronegative atoms, either by changing its hybridization or changing the atom from a carbon to something else, you'll get more and more electronegative, and we will shift any of those protons that will absorb downfield. All right, so downfield. Think going from right, to left. As you increase your chemical shift value all the way to 12, you're going downfield. And I always remember downfield is de-shielded. That means we've taken protons or electrons away from the proton and it's becoming more exposed and it will interact differently there. Okay, so I don't want to get too much into theory, but alkanes will usually absorb around 1 ppm. Alkyne hydrogens, this is a terminal alkyne, and if you have an allylic hydrogen to a carbonyl, okay, allylic hydrogens to either a C double bond O, a C double bond C, or a C double bond nitrogen. Remember what allylic means. These are vinylic atoms. They're on the double bond. If you are a hydrogen on the sp3 carbon next door to that double bond, you're called allylic. Allylic hydrogens and terminal alkyne hydrogens will usually absorb around 2 ppm. Now, this can shift a little, we don't say exactly 2. So about 1 is an alkane, and a terminal alkyne, an allylic hydrogen is around 2. Now, if you put a hydrogen on a carbon that's bonded to a more electronegative atom, like say there's an OH here, if there's a hydrogen on the same alpha carbon, remember our alpha carbons, this is the alpha carbon. If the hydrogen and the electronegative atom are on that same carbon, that hydrogen is going to be more near an electronegative atom. It's going to be more de-shielded, more downfilled. So it's going to be around 3 to 4 ppm. It could be as high as 5. It really depends. Your professor gave a good video showing how these shift last time if you want to go check that out for the last lab. Now, if you have an alkene hydrogen, that is a vinyl hydrogen directly bonded to a double bond of an alkene, you're going to be about 5 to 6 ppm. I always say high fives if you see an alkene because it's going to be around 5. Like, I know I've got an alkene, I see a signal around 5 point something, but that's where those hydrogens appear. And then if you have an aromatic, lucky 7s for you. Let's go to Vegas. Vegas, the slot 777. If you have a benzene hydrogen, you're going to absorb around 7 ppm. All right. So benzene has lots of hydrogens. Sometimes you'll see more than one absorbance there. But the absorbances are going up again. And then finally, if you have an aldehyde, hi, I'm aldehyde. The aldehyde hydrogens, the ones directly attached to the carbonyl, they usually absorb around 9 to 10. And carboxylic acid hydrogens usually absorb around 10 to 12. Okay, so this is kind of a table just showing all of that. So usually you have what's called this de-shielding factor. If you start putting the hydrogen atoms in different environments, they are de-shielded by a certain amount of ppm versus 1. 1 is kind of standard. Does that make sense so far? All right, so this table or the table from your book, they're going to be very important in your problem solving today. All right, now let's move on. The second thing we want to talk about are equivalent protons. So you have an NMR. What's going to produce a signal? The protons make the signal. But protons that are in the same chemical environment will produce the same signal. Protons that are in different chemical environments, like bonded to different things, will produce different signals. So for example, If I look at this molecule here, this is 1,2-dichloroethane, okay? I can look at that molecule and I go, gosh, that molecule's symmetric. Do you see how the hydrogens that are on the carbons, those are the protons that are going to produce the signal? They're in the same chemical environment here. Because they're both next to a CH2 bonded to a CH3, I see the symmetry there. Those are what we call equivalent hydrogens. They are all going to produce the same signal. So I'll only see one signal if I put this molecule into an NMR and run it in a proton NMR. I'll see one signal for all four of those hydrogens because they're in the same environment. Okay, now let's go to the other molecules here. This molecule has a chlorine on one side, 3 CH2s, and then a bromine on the other side. It does not have symmetry. We know bromine's more polarizable, it's more electronegative than chlorine is. So as it turns out, this CH2 is in a different environment than this CH2, even though they're both bonded to halogens. And because there's no symmetry, all three of these CH2s are going to be in different environments because of the lack of symmetry. So if I run this sample in the NMR, I'm going to see three signals. I'll see three humps, boop, 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 three different types of hydrogens. Okay, I'll do another example here. This one, I'll make it bigger. Sorry about that. I bet it was hard to see. Lo siento. If we look at this compound, it's an ester. It's got a carbonyl oxygen, and then there's a CH3 on one side and a CH3 on the other. This compound is not symmetric. The CH3, the protons bonded on this side of the molecule are bonded to an oxygen, right? A single bonded to an oxygen. All three of them. While the hydrogens on this side of the molecule are bonded to a carbon that's bonded to another carbon. Okay, so those protons are in different environments. Because of that, they have different signals as well. So we're only going to get two signals for this molecule. You'll see two signals. There's two different types of hydrogen in that compound based on their bonding pattern. All right. I think you're getting the idea here. This example, there are three signals. They're colored for you. These are from your book because I thought it would help you out to see things that you've already seen in your book before. But it gives you the number of signals. Now, when we get down here, boop, 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 to the alkenes, we've learned about symmetric alkenes and unsymmetric alkenes. Like here's a pair of geminal hydrogens. They're off the same carbon here. But if we look at this molecule has symmetry. And oops, can you all hear me? I don't know if it's cutting in and out again. I hope so. All right, because this molecule has symmetry, good. We see that about the symmetry line, kind of like when we were talking about meso compounds and stuff, about the symmetry line, these two hydrogens are equivalent to one another. So they would give the same signal. Now, if you can't see symmetry, there's a little test you can do to see if those protons are equivalent or not. This hydrogen is cis to a chlorine, trans to a chlorine, and geminal to a hydrogen. So that is cis to a chlorine, trans to a chlorine, and geminal, that means birth from the same mother, right? Gemini, on the same carbon, geminal to a hydrogen. Now, if we look at this proton, it is cis to a chlorine, it is trans to a chlorine, and it is also geminal to a hydrogen. They have the same chemical environment about that carbon. So they are equivalent to one another. So they would produce the same signal. I hope that makes sense. So sometimes if you can't see the symmetry, you can do that like cis, trans, geminal test. But these would give one signal. There's two hydrogens. They would only see one signal. Now, here's an example of an alkene that has no symmetry. Like if you cut this compound in half here, the chlorine's different than a hydrogen on either side of that mirror image. So there's no symmetry there. If we cut the alkene this way, there's also no symmetry because there's a chlorine above that line and a bromine below. So this alkene has no symmetry. These two hydrogens are different from one another, even though they're attached to the same carbon. because there's a restricted rotation in alkene. So this hydrogen is cis to a chlorine, while that hydrogen is cis to a bromine. So in this example, those two hydrogens are not chemically equivalent. One's closer to a bromine, one's closer to a chlorine. They'll give us two signals. All right. And this one we give 3. All right, so the next thing I want to talk about is integration. Now, integration, we're not going to get out our calculus and calculators here, but it does mean area under a curve, okay? And we're not going to calculate it. Our fancy computers tell us the area under the curves of these peaks, which tell us how many relative protons are producing each signal. So when you see a signal on an NMR, you'll see, okay, here's an NMR spectrum. I can see there's 1, 2, 3 signals. We usually label those as A, B, C, okay? Now, not all signals are going to have the same area under them. One signal might have a lot more area, and the next one might be smaller. The integration, the area under these curves for these two signals, might be 3 hydrogens and 1 hydrogen. 1 hydrogen's producing this signal, 3 hydrogens producing that signal. So that's called the integration, the area under the curve. It tells us the relative number of hydrogens producing a signal. Okay, now let's look at some molecules here. Here we have a 1,1-dichloroethane. It's your turn to give me some answers here. How many signals, like just what we were doing before, how many signals do you think that this molecule will produce in the NMR proton based on its structure? How many different types of hydrogen are there is another good question to ask. 2. Yes, Sheila. Is it Sheila? You are right. There is one signal here. Those 3 hydrogens are all connected to the same carbon, connected to the same hydrogen. And then we have another signal here. Okay, so I'm going to call this signal A. We just usually give them numbers. So this is HA, and these are HB. We usually give them letters, not numbers, sorry. All right, so HAs, how many of them are there? They are chemically equivalent. There's 3 HAs. So the integration under that curve would be that there's 3 hydrogens producing that signal. And here for HB, there's 1 hydrogen producing that signal. So the A and B tell us we have 2 signals. The integration tells us how many hydrogens are producing them. I could come up with an NMR spectrum here. If I have my baseline, I could say, okay, well, I know I'm going to have 2 signals. Now, this B signal is going to be, it's got some electronegative atoms bonded near it, so it's going to be more downfilled, which means to the left. So that 1 hydrogen height will be more downfilled to the left in our ppm, and then the 3 hydrogen signal will be higher and to the right. It'll be a 3-to-1 ratio of those. So I'll see 2 signals with different integration. All right. Now, sometimes this gets interesting. Let's see if I can go up here. Let's look at this molecule. Now, be very careful. We're looking at protons in the same environment. How many different signals do you expect to see from this molecule? Protons. We're only looking at hydrogen here. Cuidado, my friends. 2 again. Very good. We have the CH2s. Those are hydrogens on a carbon that's directly bonded to a chlorine. And then we have the 2 CH3s that are giving the same signal. They're both hydrogens on carbons connected to the same carbon. So they're in the same environment. So I'm going to call these HA, and I'm going to call these HB. Now, which one will be more downfilled or de-shielded? A or B? Which one will have a higher chemical shift? It'll be B, right? Is that what y'all are thinking? Sorry, I jumped the gun. It'll be B because it's more near the chlorine, right? These hydrogens are another carbon away. These hydrogens are on the same carbon as the chlorine, so they are more de-shielded. So when I go to look at this, though, if I look at the integration, for signal B, there are 2 hydrogens producing that signal. For signal A, how many hydrogens are producing that signal? Yes, 6. So we've got 6 hydrogens here. If I go and I think about what the NMR is going to look like here, a 6-to-2 ratio is the same thing as a 3-to-1 ratio. Here's where it gets interesting. Notice that I said that the integration is always the relative number of protons. Sometimes we're not given the exact amount of protons, we're given the ratio. But if I have a molecular formula and I know I have 8 hydrogens, if the integration is 3-to-1, let's say 1, 3, but I know that I have a total of 8 hydrogens in my molecular formula, sorry, then I can say, well, 3-to-1, that only equals 4 total. This is just 4 times 2. So if I multiply both of these times 2, this is actually 6 hydrogens and 2 hydrogens producing my signal. And that would be what that looked like. So we've looked at a few things now as far as trying to set up starting to read and interpret NMRs. The first thing is we say different types of protons absorb at different places. The more deshielded you are, the more downfilled. And we can use this chart to determine where our hydrogens are typically going to absorb versus what they're bonded to. Then we said we can determine how many signals we have, tells us something about the bonding pattern of our molecule. Okay. Some protons are equivalent. So just because you have 10 protons or hydrogens in a molecular formula doesn't mean you're going to have 10 signals. A lot of times you're going to have less signals because some are equivalent. And the third thing we said is that when you look at an NMR, usually those signals are integrated, meaning you can tell how many hydrogens are on relative scale producing each signal. So here's an example of that. All right. This compound is, I'll just draw it out here. It's tert-butyl methyl ether. And so I'm going to draw this out a little bit better so we can see it. Here's the compound. It is an oxygen with the C, with the CH3, and a CH3 bonded. And then on the other side, we just have a CH3. So it's a methyl and a T-butoxy group on ether. All right, now, if we look at this molecule, we can say, well, there's 2 types of hydrogens here. These 3 hydrogens are equivalent to one another. They'll produce one signal. We'll call that A. And all 6 of these hydrogens are produced, it's 9, isn't it? That's a CH3, by the way. I have horrible handwriting. Ugh. If only I was born with good handwriting. I have to practice. But all 9 of those hydrogens produce the same signal. We'll call that B. A lot of times, instead of circling these, what we just do is we write B, B, B next to them so we don't have to messy up our structure. But there's 2 different signals here. But we know the integration of signal A will account for 3 hydrogens, and the integration of signal B will account for 9 hydrogens. Now, 3 to 9 is the same thing as what in its lowest ratio? 3 to 9 is equal to what in its lowest ratio form? Yes, 1 to 3. So sometimes instead of seeing a 3 and a 9 as the integrated area, you'll see a 1 and a 3. So when I run, or I didn't do this, someone else did, ran the NMR. Now, I didn't talk about this a second ago, but at 0 ppm, we have an internal standard called tetramethylsilane. That's never part of our sample. Our samples start above 0, okay? So that's not a part of a sample. But we have 2 peaks here. We have the T-butyls, which are further away from the oxygen, so signal B here, and those will be more upfilled because they're more hydrocarbonous. They're standard alkanes. They're around 1. And then the ones that are bonded to the oxygen, that electronegative atom, are around, 2 to 4. So this is signal A. And if we look at the relative areas, we see it's 3 to 1. Okay, so that's what the integration will look like. Usually the integration is marked near the signal so you can see how many hydrogens are producing it. Now, what if I go backwards here? What if somebody didn't tell me what compound I have? Okay, here's what I can do. If I know that If all I see is this, so imagine I don't see anything else, okay? I'm just looking at an unknown and I see an NMR. I've got two different signals here, so I've got two different types of hydrogen. If I see the integration is 3, to me that always means a CH3. A 3 means three similar hydrogens producing that signal. If I see a 1, a lot of times that tells me I have a CH. Just a CH. Now here's the kicker. If I'm given the molecular formula, 1, 2, 3, 4, 5 is C5, AH9, is it 11? 12. 12O. That molecular formula usually came from mass spec, right? We can figure that out. But if I'm given the molecular formula and I know I have 12 hydrogens, I can go, wait a second. 3 to 1, that equals 4. I don't have a 3 to 1 with only 2 signals. 12 divided by 4 equals 3. So I have, instead of 1, if I multiply this times 3 and that times 3, what I really have is 3 hydrogens producing this signal and 9 hydrogens producing that signal. So you'll usually be given enough information like a molecular formula to where if the number of hydrogens total don't add up, you can multiply to make them equal to what you have. I hope that makes sense. So I would say, okay, wait, that's 3 hydrogens. 3 hydrogens is a CH3. That's a CH3 on the molecule. And then if I have 9 hydrogens, you can't have a CH9. Like, please don't ever write that. You'll make organic chemists cry real tears if you wrote CH9. What you have are 3 CH3s that are equivalent to each other, right? So usually the way it works is if you have an integration of 2, you probably have a CH2. If you have an integration of 1, you have a CH or an OH. If you have an integration of 3, it's a CH3. And if anything higher than 3, you probably have multiples. Like if I had an integration of 4 on a curve, I wouldn't say CH4 because it's probably part of a molecule. I would probably say I have 2 CH2s that are equivalent. Kind of like that first example we looked at. It's 2 CH2s. So I'm just going to use simple math there and come up with those probabilities. Okay. Now, this means that right now, based on where something is on the chart, we can kind of tell what it's bonded to if we know what atoms we have in molecular formula. The number of signals tells us something about the symmetry of the molecule and how many hydrogens are alike versus different. And then the integration tells us how many hydrogens are producing each signal on those carbons. This is all going to add up to very easy problem solving. The next part of the puzzle, have you all heard of splitting yet? Spin splitting? Have y'all gone over that at all? Okay, no. So you are drinking from a fire hose today. Okay. So for spin splitting, what happens is, so far, when I tell you we're looking at an NMR signal, I'm just making a signal and it has one tip at the top, okay? One peak, we call it. So whether it's a broad peak, so sometimes hydrogen bondings makes things rounded and broad, but most of the time these peaks are like come to a point at the top. I have not told you so far that neighboring hydrogens can split our peaks. What I mean by this is if you have a hydrogen that's all alone, okay? So here's a hydrogen, it's bonded to a carbon or something, but there are no other carbons. So here's this hydrogen, it lives in this carbon's house. This is the hydrogen producing the signal, okay? Now, if we go to the carbon next door, this is like the carbon is the house, the hydrogens live in it, okay? Then if there are hydrogens on the carbon next door, we would call those neighboring hydrogens, right? Just like if you live in your house, you're the hydrogen inside of your carbon or bonded to your carbon. But if somebody lives in the house next door, directly next door, they are your neighbor, okay? So if you have hydrogens on the carbons next door and you're looking at that signal, those hydrogens can split your signal, okay? Neighboring hydrogens. So signals are split by neighboring non-equivalent hydrogens. It has to be a hydrogen that would have a different signal, okay? And we'll get into that in a little bit. But let's say that I have this structure right here. I'm going to blow this up a little bit. Okay. This hydrogen, let me get my eraser out because, is there an eraser? Okay. I don't know if there's an eraser. But anyway, this hydrogen, I'll change colors, is on this carbon right here. So let's say we're looking at that hydrogen and it's producing a signal. Well, if I go to the carbon directly next door, this is called the neighboring carbon. Notice there are no hydrogens on the neighboring carbon. So on the neighboring carbon, hydrogens equals 0. Okay? Now, the way the splitting of this original signal works is the number of peaks on that absorbance will equal the number of neighboring hydrogens plus 1. Okay? So if this hydrogen has 0 neighbors living next door, 0 neighboring hydrogens, 0 plus 1 equals 1. This hydrogen will only have 1 peak in its NMR, is what that means. So if you come over here, it'll just have 1 peak. Now, a lot of times it comes up and it goes back down. These are just lines, but only 1 peak. You are called a singlet. This is the splitting pattern of that signal. So you count the peaks and go, that one's a singlet. Now, if you're a singlet, you can figure out how many neighbors you have next door. Then the splitting pattern minus 1 equals your number of neighboring hydrogens. So if I see I only have 1 peak, 1 minus 1, I have 0 hydrogens on the carbon next door. That is called a singlet. So here's what I would do with that. If I saw a singlet, like in an NMR spectrum, oh, look, there's only 1 peak there. Singlet minus 1 equals number of neighboring. I'd say, okay, I've got a CH here. The neighboring carbon has no hydrogens on it. That's what I would do. I would put no hydrogens there. All right. Now, what happens if you have some other scenarios? What if you have neighbors? All right. If you have neighbors, you're going to start splitting your peaks. So I'm going to come over here. If we are looking at the signal, can you all still hear me well? I just want to make sure. Because I know y'all can't see me. All right, good. If we're still looking at this hydrogen and we're like, okay, this hydrogen is going to produce a signal right there. That's the one we're looking at. And I know it's going to produce a signal. And I want to know how many peaks that signal is going to have. It's the number of neighbors plus 1. So if I look on the carbon next door, it turns out there's 1 hydrogen on that carbon next door. The number of neighboring hydrogens equals 1. So if I look and I say 1 neighboring hydrogen plus 1 equals my number of peaks, that's your splitting pattern. That's going to equal 2. So I'm going to have this hydrogen, it's going to give 1 absorbance, but it's going to have 2 peaks. That's called the splitting pattern. Number of neighboring hydrogens plus 1. So what's going to happen here, disregard that J, we're not even going to get into that. But you will see that you will come up off the baseline, you'll come to a peak, you'll come back down a little bit, but not all the way. You won't fully resolve, and you'll come back down. So from where you come off and on the baseline, that's still 1 signal. You didn't come all the way back down, but you have 2 peaks. That is called a doublet. It's like a D. Now, if you see a doublet, that's 2 peaks. If you subtract 1, that's your number of neighboring hydrogens. So if you see a doublet and subtract 1, 2 minus 1, I have 1 neighboring hydrogen. So this is going to help you. Because if I'm looking at an unknown spectra and I see, okay, I've got like a 2 hydrogen, let's say, let me come back here. I'm going to come over here. I drew a line. I didn't even do it. Let's say that I have this peak and it's a doublet. Sometimes they look like that, okay? And let's say the integration here is 2 hydrogens. All right, now we're getting more clear here. So this is the integration. That's how many. Now, the integration tells me how many hydrogens are producing that signal. If I see the integration is 2, I'm going to say I probably have a CH2. That is producing this signal. So this is signal A. Now, the splitting pattern, the number of peaks, there's 2 of them minus 1 tells me how many neighbors I have. 2 minus 1 equals my neighboring hydrogens. I have 1 neighboring hydrogen. So a doublet has 1 neighboring hydrogen. So what I'm going to do is I'm going to say, okay, the carbon next door has 1 hydrogen and some other stuff. Do you see how now we're getting to the point where if I'm given a signal, I can start putting parts of the molecule together? This CH2 is connected to a CH next door. And then I can go find this CH and I can see what it's connected to by its splitting pattern. It's going to be really interesting, okay? So what are some other examples that we can look at? If you are a hydrogen producing a signal, okay, here's your CH, it's producing a signal, and the number of neighboring hydrogens next door, here's our next house, go to the carbon directly attached, is 2. So number of neighboring hydrogens equals 2. Your splitting pattern equals the neighboring hydrogens plus 1. It's called the N+1 rule. Your splitting pattern for this signal will be 2 plus 1 or 3. You will have a triplet. And then we kind of start naming like kids, quartet, quintet, all that good stuff. But that means you have 3 peaks at the top. Does this make sense, kind of what I'm doing here? So here's what a triplet will typically look like. I'm going to skip that image. But a triplet, they're always symmetric if it's normal splitting patterns. Notice the symmetry here. They're not always completely symmetric, but they're kind of symmetric. But we've got 1, 2, 3 here. That's a triplet. So if you see a triplet, 3 minus 1 equals 2. That's your number of neighboring hydrogens on the carbon next door. And so you can have a triplet. A T is usually how we represent a triplet. If you have 3 neighboring hydrogens, that will produce a quartet, a Q or a QT, if you like cuties, citrus, but so on and so forth. But that's what's going to end up solving our problems for us to see our ultimate connectivity. So here's a basic example, okay? Here's a compound. It's a tribromo compound, and we see that there's 2 different types of signals here. So these 2 hydrogens, this is a CH2, really, if we condensed it down. Those 2 hydrogens are equivalent to one another. They would produce, let's call it signal A, because they're equivalent. They're both on the same carbon, connected to the same environment. The blue one is on a different carbon, and it's signal B. So this is where it gets fun. We can kind of try to figure out what the NMR is going to look like, okay? Now, we've got 2 signals. The signal in blue is 1 hydrogen, so we'll have an integration of 1. That's its area under the curve, how big the curve is. The one in red, there's 2 hydrogens producing it. So I would say that was a 2 hydrogen signal, and B is a 1 hydrogen signal. Now we're talking like an NMR chemist. I've got a 2 hydrogen over here, I've got a 1 hydrogen over here. All right, now let's see how they affect each other. When I look at the one in red, I would call this a 2 hydrogen something. Now, the one in red, its neighbor has 1 hydrogen. So your splitting pattern is 1, or the number of neighboring hydrogens plus 1. Let's remember that. Splitting equals number of neighboring hydrogens plus 1. So when I say what will that signal look like, if I've got 1 neighboring hydrogen for that red one, it will be a 2 hydrogen doublet. It'll be a 2 hydrogen doublet because it'll be 1 plus 1. Okay. Now, if I go over here to B, that one we would call a 1 hydrogen because there's 1 hydrogen producing the signal. That's its integration. But now it has 2 neighboring hydrogens. How many peaks is that signal going to have if it's got 2 neighboring hydrogens? Yes, 3. So 3 is called a triplet. So I would say that signal is going to be a 1 hydrogen triplet. Okay, so I can start to make what the NMR is going to look like so I can verify this compound is what I think it is. Okay, then I run the NMR and it looks the same. Now there's one other thing, downfilled and upfilled. This hydrogen is closer to 2 bromines, the more electronegative. It's going to be more downfilled. So when I go to look at this on the NMR, notice there's 2 signals here. This will be more downfilled because it's closer to more electronegative atoms, and this one will be more upfield. So the downfield one is closer to the left. This is a 1 hydrogen, and if I look closely, see how it's got this box, that inlay? It's blown up for us so we can see the splitting. This is a 1 hydrogen triplet at around 5.7 ppm. That's its chemical shift. So if someone wants to know the chemical shift, you read the x-axis. At around 5.7 ppm, I have a 1 hydrogen triplet. And then we would say over here, okay, we're around 4.1 ppm. That's the signal. That's the chemical shift. So at 4.1 ppm, maybe the integration's given up here, 3. I would say I have a 3 hydrogen. And then here, if we look at the expanded, there's 2 peaks. We have a 3 hydrogen doublet. See how that works? So we can start to talk about the peaks. I can say at 5.7 ppm, I've got a 1 hydrogen triplet. That's telling you the integration, how many hydrogens are making the peak, and it's telling you basically how many neighbors. Splitting -1 gives you neighbors. All right, this is a lot, I know. All right, now, here's another example, okay? If we look at this as our last NMR example before we practice a problem, I want to practice a problem or two before you go today so you can see how to do the assignment. And you always have your book in this video to help if you need, and some other, YouTube's always good too. I'm not going to lie. All right. So in this compound, this is 1-bromopropane. If we look at 1-bromopropane, we've got the hydrogens that are closest on the carbon to the bromine. And then we've got hydrogens that are next closest, a little bit further. And then we've got the hydrogens that are the furthest from the bromine. All right. Okay, so we're going to have 3 signals here. We're going to call these A, B, and C. So I've got signal. Oops, that one's called C. C, B, and A. Then you can choose whatever letters you want. No one's going to kill you if you call CA and AC. We're organic 1 students. But we've got 3 different signals. Now, signal A, B, and C are going to have integration. So now we know the number of signals we have. And we know each signal will be the number of protons that produces. So signal C will be a 2 hydrogen signal because there's 2 hydrogens. Signal B will be a 2 hydrogen signal, okay? And signal C will be what will signal C be? Yeah, 3 hydrogens. You got on. All right. So a 3 hydrogen, oops, that was the most horrible 3 in my life. Okay. 3 hydrogen signal. Now we know more than this now because we have the structure. So I can figure out what the NMR is going to be, and then we'll work opposite. We'll start working opposite in a little bit. But it helps to figure out NMRs before you start trying to solve unknowns. So that's why this is important. Now, if I look at this molecule, okay, these hydrogens are producing a 2 hydrogen signal. How many neighbors do those hydrogens have in a different signal? So how many neighboring hydrogens does that pink one have? Let's see. How many neighboring hydrogens does C have? Yes, it has 2, because directly next door, we've got 2 hydrogens on that carbon. Very good. You are right. So if I know that next door I have 2, 2 is my neighboring plus 1, that's gonna be a 3-peak signal. Now 3 peaks we usually call a triplet. So I'm gonna call that a 2 hydrogen triplet. Okay. Now let's go to peak A, or signal A. Okay. Signal A is 3 hydrogens are gonna make that signal integration. How many neighbors does signal A have? How many neighboring hydrogens? 2, yes. And because it has 2 neighboring hydrogens, we're going to use the n+1 rule. We're going to have a triplet again. So we're going to have a 3 hydrogen triplet. So this is how we're going to be able to tell these peaks apart. The A is a 3-hydrogen triplet. C is a 2-hydrogen triplet. Now this is where it gets fun. B has how many neighbors? How many neighbors does B have? Yes, it has 5. Very good, guys. So because we have 5 neighbors, remember our n+1 rule is our splitting pattern. How many peaks are we going to have for that signal? 6. And a 6 is called a sextet. And we usually, when we get higher than a quartet, we write it out. So sextet. Or you could just say 6 peaks. It's all good. No one cares. But we're going to have a 2-hydrogen sextet. Now, just looking at this molecule, who's going to be the most downfield signal? The one that's most de-shielded by electronegativity, A, B, or C? C is downfield. Very good. So this one's going to be the most downfield. That means the furthest to the left. Okay. And then which one's going to be most upfield or more standard like a regular alkane? It's far away from electronegativity. That would be A. A is going to be more upfield. All right. So then B is going to be somewhere in the middle. Now let's pull this back and let's look at our spectra here. Okay. Based on what we did. So notice there are 3 signals, A, B, and C. Okay. Signal A is we said the most upfilled. This is signal A. It's the one that's closest to 0. It's around 1 where alkanes usually are, alkane CHs. Now its ppm, it's about 1 ppm. And if we look at it, the integration is not given, but it is a 3-hydrogen. But if you look here, it's a triplet. So this is a 3-hydrogen triplet. All right, now we can find B. B is somewhere in the middle. This is signal B. It's around 2 ppm. And I'm just going to tell you it's a 2-hydrogen. The integration is not given on this one. It's a 2-hydrogen. And if we blow that up, there are it's kind of symmetric here. There are 1, 2, 3, 4, 5, 6. There are 6 peaks on that. It's hard to see, but that is a sextet. So we have a 2-hydrogen sextet, just like we thought. And then if we look at the third one, it's around 3.4. I'm not going to get that close to see it, but the integration's not given, but it could be. It would be a 2-hydrogen. So 3.4 ppm, we have a 2-hydrogen, and it's blown up for us, so we can see it's a triplet. There you go. We could figure out what that NMR should have looked like at just by observing the molecule. Okay. Now what we have to do is we have to start doing things in reverse. Now I'm going to skip carbon NMR for now because it really doesn't tell you much. It's not very useful. You can get along without it. But what I want to do, because we have about 25 minutes left, I want to use everything we've learned today to start solving some problems. Okay. So let me find. That's not it. Is that it? Let's see if this is it. Okay, that's not it. Let's see here. Let me load a problem real quick. Let me take back ownership of this on my computer. Let's work a problem. So I need to manage my presentations. Gotta add one. I've got to find it real quick. So many files, so little time. Let me see what it's called real quick. Un momento, por favor. You know what? Let's do one of your lab things together. What do y'all think about that? You have 4 lab problems, but because you're a little newer at this, I'm going to upload them if I can find it. Okay, there it is. Upload. All right, hang with me. It's got to come up. Is it coming up? Okay, there we are. Here's your lab. Now, this lab is found under NMR 2, like a Roman numeral in your lab this week. But it's got a little bit of background. We went over a lot more than that. But what I want to do is I want to start going over some problems. So we're going to do, there are 4 unknowns, and you have an unknown sheet that you can fill out. And you'll fill out all this different information based on what you're given. So there are 4 unknowns, A, B, C, and D. We're going to do A together, okay? And the unknowns have some combustion data. Let me take back my iPad so I can highlight this. All right, they're going to have some combustion data, okay, for each. And then you're going to be given a mass spec. And then you're going to be given an IR. And then at the end of the packet, so each of them have a composition, your combustion data, your mass spec, and your IR. And at the end, they will have an NMR, a proton NMR. And so we're going to do A, and I'll have to hunt through and find the NMR later. So you'll do B, C, and D at home. And there's an NMR report form for each of these where you'll just show your work and you'll fill it out. If you don't have a printer at home, no sweat, my pet. You can use a piece of paper and kind of just follow the form on a piece of paper and upload it to the NMR2 assignment. Does that make sense? So if you don't have a printer, just solve the problem on a blank piece of paper and you'll just turn it in online. Is that okay? Do y'all understand what I mean? All right, so let's get to solving problems. We're going to do A together. Now, the first thing we need to do is, all we know about this compound is it's unknown A. We need to get a molecular formula first. So the first thing we're going to do is we are going to use the composition, percent composition, and the mass spec together to get a molecular formula. So we're going to get a molecular formula first. Then we're going to figure out our bonds that are in our molecule and our functional groups. Now, remember what tells us what kind of bonds we have. That's the IR. So combustion and the IR will tell us our bonds, okay? And then once we know what functional groups we have and how many carbons and other things we have to work with, we're going to look at the NMR to tell the connectivity, to get the exact identity of the molecule based on its integration and splitting patterns and where the signals show up, okay? What's bonded to electronegative stuff and what's not. And so that'll be NMR. All right, let me get rid of that because it's covering our CHN data. So let's start with the first one first. We've got a composition, a percent composition of 54% carbon, 9% hydrogen, 36% oxygen. That's given. Now, if I look at the mass spec, the only part we said we were really interested in is our final mass cluster, which has our molecular ion in it. Do y'all remember that? All right, so our molecular ion, if we read here, and it's probably small to see on your screen. So when you get the PDF, you'll be able to see it. But this is 80, this is 90, and that's 100. It's 88 is its MZ value, the mass to charge ratio. So 88 AMU is the weight of our molecule. That is equivalent to 88 grams per mole in mole form, because AMU and grams are equivalent if you assume a mole of the compound. All right, so what we're going to do is we are going to calculate the molecular formula first. So I'm going to switch over, I've got the numbers in front of me. So, but what we're going to do is we're going to use that data. We're going to start with, so we're going to calculate the molecular formula. We're going to start with the 88 grams of our compound per 1 mole of our compound. So we've got 88 grams of our compound. That's the whole mass. Now we're going to multiply that, I don't use parentheses, times the percent out of 100 grams of carbon. So we've got carbon, we've got hydrogen, and we've got oxygen. So we're going to start with the total weight of our compound for all of them, 88. We're going to multiply times the percent. So the percent carbon was 54.53. Now, that's percent. So that's out of 100 grams of compound, that's how many grams of carbon is in the sample. The percent hydrogen, I know it's not in front of you, was 9.15% hydrogen. But we'll convert that to grams because the percent is out of 100. Do y'all see what I'm doing? We're converting the total weight of the compound to the weight of each atom. And so we know we have oxygen in our compound too. So our oxygen's weight, or percent, was 36.32 grams of oxygen, considering that we have 100 grams of compound. So all of these are grams of compound. All right. If you're writing this down, I'll give you a second to catch up. This would be something on your report sheet that you would do on the back of the page and then report your molecular formula and SODAR on the front. But we're going to get the molecular formula. Now, from here, we're going to multiply times 1 or divide by the molecular weight of each of these atoms. Carbon weighs 12.01 grams for every 1 mole. Hydrogen weighs 1.01 grams for every 1 mole. And oxygen weighs about 16 grams for every 1 mole of oxygen. Okay, so this is carbon, hydrogen, oxygen. All right, now if we use our unit analysis, I like to knock my chemicals out, my units out. The grams cancel, and then the grams of carbon cancel. We're left with moles of each. So I'm going to calculate for you. Wham jam, thank you, ma'am. We end up getting 4 moles of carbon, 8 moles of hydrogen, and we end up getting 2 moles of oxygen. That's an O, not a 0. Now, if we put all of this together, what we have is a molecular formula. Assuming 1 mole of compound, we have C4H8O2. That is our molecular formula. So on our report sheet where it says formula, we would put the calculations on the back. We're going to put the formula on the front. So this is for A, just by the way. All right, now, the next thing we can always do with that, remember, anytime you have a molecular formula, get a SODAR. The SODAR is the number of double bonds and rings that your compound could potentially have. So if I remember, we've got SODAR, it's going to equal 2 times the number of carbons. So 2 times 4 plus 2, okay, because I've got 4 carbons. Now we're going to minus things that get 1 bond. So we're going to now subtract our 8 hydrogens. And then we don't have any nitrogens or halogens, so we'll just divide this number by 2. All right, so if we look here, we've got 2 times 4, that's 8, plus 2. Y'all help me with my math because I mess up all the time. Okay, 8 plus 2 is 10. Minus 8 is 2 divided by 2. Is that what you all got, or did I mess up? Is that right? 2 divided by 2? Yes, okay. So that means our SODAR is equal to 1. That's our SODAR. That's our degrees of unsaturation. I either have 1 ring or 1 pi bond in my compound, but I can't have both. Okay? So that is the first thing we needed to solve this problem. Okay? On your report sheet, that'll be under formula. Now, the next thing on your report sheet is structure. We don't have the structure yet because we have to solve for that. So we're going to go back to our lab. I'm going to pull that back a little bit. We're going to go, we're done with the mass spec now because we got the molecular formula from those 2 pieces. Now we're going to the IR. Oops. Okay. The IR, I'm going to blow it up a little bit so we can see what's going on. Now, remember what you need to do. You make your life simple when you get an IR. You find the fingerprint region and promise you'll never read past it. So the first thing I always like to do if I'm given an IR is I find 1500. So on my x-axis here, 1500 is about right here. And I say, Julia, don't read that. It's fingerprint region. That's where all the carbon-carbon and carbon-nitrogen single bonds and things are, and it's confusing. So now we've really actually simplified our structure here. Does that make sense? Doesn't this IR look a lot more simple now that we got rid of the fingerprint? Now, how many different absorbances do you see from the baseline? Now, baselines aren't always clear. They're not always lines, but this is the baseline. Stuffed up domes. How many different absorbances do you see? Yes, we see 2. So from that baseline, I've got an absorbance here, and I've got an absorbance there. Now, what is here and there? We have to look at the wave numbers, okay? So the wave numbers are on the x-axis for our IR. So I see, let's see here. I've got all my stuff in my lap. Okay, I see that if we look, remember how there were 5 regions? There's really nothing around 3,500. By the way, sometimes you see something like that in your baseline. That is usually water in the sample. And you see a lot of it when we live in Florida because it's so humid. But I don't see anything coming down. So I don't have anything like OHs or NHs around 3,500. So my next zone, remember, was 3,000. And if we look at that 3,000 line, all of that is just below 3,000. So do we remember what's below 3,000? It's pretty common. Yes, it's our sp3ch stretches. So that is going to be, so it's just below 3,000 reciprocal centimeters. That's our sp3ch stretches. sp3 means alkane. So we have alkane, that's a hydrocarbon backbone. Now, let's go to the next signal. It looks like it's between, here's 1,700, okay? So it looks like it's about between 17 and 1,800. Let's call it 1,750. We don't have to be exact. No one's going to harm us if we're not. But around 750 reciprocal centimeters, what absorbs there? And it's pretty intense. That is a strong absorption. Yes, the carbonyl. All right. So look what we just found. That's the CO double bond stretch. We just found our SODAR equal to 1. We have a pi bond, not a ring in this compound. So that is our 1 degree of unsaturation. Our SODAR equals to 1. So we have 1 pi bond. Now, I'm going to go back and I'm going to show you how to log this on your data sheet, okay? So I'm going to come back here. I'm going to pretend this is the data sheet. The second part, after structure, it will have IR peaks. And there's going to be a box. And it will say wavelength, blah, blah, blah. I spelled it wrong. That's what I get for trying to go fast. It never fails. I do everything messy. I promise that says wavelength. Just don't put it in a court of law on me. All right, and then we've got bond over here. So we're gonna, this is like if you were in the lab and you had to keep a lab book of your data, you can actually keep a data table for IR peaks. So this is what you would put in there. Now it's got a couple boxes there for us. This is, remember, this is compound A still. Now, we said that we saw an sp3ch stretch at just below 3,000. Oops, wait, I put that in wrong, didn't I? Lo siento. Okay, the wavelength is just below 3,000 reciprocal centimeters. The bond, we said, was an sp3ch bond. Sorry about that. All right, now, the second one we said was about, we don't have to be specific, but about 1,750. It could have been 1,720. Potatoes. But we said that was definitely a carbonyl stretch. All right, now let's keep in mind what our molecular formula was, okay, guys? Because this is going to be important. Our molecular formula, gosh, I already forgot. Does anybody remember what it was? C4 something, H, oh gosh. Was it H8O2? Okay. Now, here's where it gets interesting. We have 2 oxygens. We only see 1 carbonyl. Now, what are our carbonyl functional groups? We have to kind of start thinking like we've been in organic chemistry all semester. Different carbonyl functional groups are ketones, aldehydes. Do y'all know the difference? Ketones are carbonyls in the middle of a chain. Aldehydes are carbonyls at the end. But we also have a carboxylic acid. And there's one more. Well, there's two, but we don't have nitrogen in our compound. Carboxylic acids have 2 oxygens. Ketones and aldehydes do not have 2 oxygens. So I'm going to get rid of those. Notice we have 2 oxygens. We can either have a carboxylic acid or an ester. Do you remember what an ester is? So a carbonyl OH is a carboxylic acid. A carbonyl O in the middle with another carbon bonded to it is an ester. Which one do we not have based on what we saw in the IR? Did we see a big hairy beard sitting on top of our thing? Like, oh, there's Santa Claus. Yeah, we did not see that very broad OH. So what wasn't there was an OH. And I point this out, okay? Because underneath your peaks that are missing, we have 2 oxygens. So we know that. But there's a part of your lab where it says missing. And you can think about what wasn't there that led me to my decision. There was no very broad OH of a carboxylic acid. So what I am going to say is that based on this data, we have an ester. Because that has, oops, there's an oxygen there. That has 2 oxygens, but would explain the CO bond is a single bond. And in the ester, a CO single bond is in the fingerprint region. We can't identify it because there's so much stuff going on. All right, so I'm going to go back to our lab. Okay, so we've got, see, there's a CO stretch down here. We just can't see it. So we're going to go back and say we have an ester. Keep that in mind. We have an ester. Now, we're going to go on. I'm going to go find the NMR because the NMR is going to tell us what type of ester we have. Unknown C. Okay, unknown A. So if you go a few pages over, you will find your NMRs. This is a proton NMR, 1H NMR for A. Okay, now we don't have the molecule yet, but we have some information. Let's remind ourselves we're C4H8O2, I believe. I hope that's right. And then we have 1 degree of unsaturation, and we think we are an ester. Now, instead of writing ester down, here's what I'm going to do to help myself out. An ester, oops, let me make, yeah, an ester has a carbonyl and an oxygen. Now, how many more carbons do we need to put on this ester to fulfill our molecular formula? 3 more. All right, now we've got to put 3 more carbons on. In order for it to be an ester, there must be at least 1 carbon on each side. True? Yes, that's the definition of an ester. So now I only need to figure out, just based on what an ester is, where the 4th carbon goes. Now I have 2 options. Either the 4th carbon is on this side, on the oxygen side of the ester, or the 4th carbon is on the carbonyl side of the ester. Now, what in the world is going to solve this problem for me? It's going to be the signals and where they're found, their ppm. It turns out that if you remember back to the NMR chart, which you probably don't have memorized, that's okay. You're going to use that chart to solve problems. Kind of like you use a periodic table, you're going to use that chart, okay? But if there is a hydrogen on the carbon on the oxygen, that's going to be more downfilled than a hydrogen on an alpha carbon or allylic to a carbonyl. An allylic carbon hydrogen is going to be around 2 ppm, 2 to 3, usually around 2. The ones that are hydrogens that are on the same alpha carbon as oxygen, their ppm is going to be about 3 to 4. Okay, so they're going to be around 3 to 4, a little higher. Okay, so we have 3 signals in our NMR. We have signals A, B, and C. Do y'all see that? Now that is at 0. That's TMS. That's an internal standard. That's not part of our thing. Now this is probably water. That's a blip. That's not a, this is a real spectrum. It's got real impurities. But we have 3 real signals here you can tell that are absorbing. Now when I look at the first signal, there are integrations given. They're at the top of your spectra, okay? I'm going to bring them down so we can see them. If this is signal A, okay, signal A is a 2 hydrogen. And how many peaks does it have? You can kind of see it, but can y'all count how many peaks A has? 4. Yep, so it's a 2 hydrogen quartet. Now, if I see 2 hydrogens, you know what my mind's going to tell me? I've got a CH2. Okay, now look where that CH2 is. This is the most downfilled signal. If you have an ester, the hydrogens that are most downfilled are going to be found on the oxygen side, the pink side over here. Okay, so what I have is I have 2 hydrogens bonded directly to an oxygen. Okay, now that's producing signal A. So we'll call the signal A. Now, what are they being split by? Well, it's a quartet. So if you subtract 1 from that, how many neighboring hydrogens does it have? 3. Okay, now this is where it gets fun. All right. If I have 3 neighboring hydrogens, can this oxygen have 3 neighboring hydrogens? No, oxygen is not a house. Carbon's a house, and carbon houses our neighbors. So if I can't have 3 hydrogens on that side, I am next door on this side. So this is signal A, okay, and it has 3 neighboring hydrogens. 3 neighboring hydrogens is a CH3. So I've already figured out my compound, if you can figure this out, because if this is the most downfilled signal up here and it's CH2, it's next door to a CH3. But we're going to confirm this, okay? Let's go on a little further. Okay, so that's a CH2 next to a CH3. That is signal A. Now, signal B. Signal B, how many peaks does it have? It just has 1 peak, right? Signal B there. All right, so it is a singlet. So this is it's 3 hydrogens. This signal B here is a 3 hydrogen, that's its integration, singlet. Now, if you're a singlet, subtract 1, how many neighboring hydrogens do you have? 0. All right, so what this is telling me is that this signal is a CH3, and it's next to no neighboring hydrogens. Now on the ester, because by definition of an ester, we are probably this CH3. It's just a singlet. It has no neighboring hydrogens. It's at the end of the chain next to a carbonyl. Okay, and then that brings us to our final one. So that would be this signal C. Now this signal C, it's got a 3 hydrogen integration. So it's a 3 hydrogen, and it looks like, for sake of time, it's a triplet, right? 3 peaks. So it's a CH3. If you're a triplet, how many neighbors do you have? Subtract 2. Yes. So subtract your splitting pattern. That's how many neighbors you have. This is a CH3 group that's next door to a CH2. Now we can't keep adding hydrogens. This CH3 is the one that was splitting our CH2 earlier. So this is the CH3 next to our, oops, I lost a hydrogen, our CH2. So those 2 signals are splitting each other, okay? That is the compound structure. So if we come back, now I'm going to go and I'm going to show you how this looks on the report sheet, okay? So I'm going to go to the NMR report sheet, and I'm going to show you what it looks like in our last few minutes. We're almost done, yay. So for NMR, you are going to have your proton. You are going to have your chemical shift. I'm going to write it like that, ppm. You're going to have deshielded by, and you're going to have split by. All right. And it's like a grid. So you're going to put some data in here. Okay. So I'm going to propose our structure. I made this a little big, but I'm going to put it in red so we can see it. So we said that we think that we have oops, there's an oxygen there. And then a CH3 on this side. So we said that the most downfilled peak, the one next to the most electronegative atom, that oxygen, that was a CH2. And it was a quartet, which means it had 3 neighbors. So it was next to the CH3. Okay. So we think that this is our structure. So what I'm going to do is I'm going to go back just like we did earlier. We're proposing this structure, and I'm going to call this hydrogens A, hydrogens B, and hydrogen C. So those are my protons. So I'm going to go to hydrogen A real quick. Proton A, that's represented by this structure that you're going to draw. You're saying, I think this is my compound. So that's proton A. Now, its chemical shift was about, what was it? 2.0 for a sake of time. It was the one in the middle, okay? And so it was deshielded, that hydrogen, that CH3 was shielded because it was next to a carbonyl. The carbonyl is what gave it its ppm. So it was deshielded by that carbonyl. So I'm going to put, okay, that CH3 there is deshielded by the carbonyl. And then it's not split by anything. It was a singlet. So it did not have anything it was split by. So it had no neighbors. Now I'm going to go to B. B was this one. If we look back at the signal we called B, B was most electronegative. So it was the furthest downfield. Its ppm, if we look, was about 4.1. Okay. So 4.1 is the most downfilled. And so why was it the most downfilled? That CH2 was deshielded by an oxygen. That CH2 was next door to an oxygen, which made it very downfilled because it's electronegative. So that's why it was the most downfilled. And then what was it split by? It was split by signal C. B was split by C over here, the CH3 group, which is why that compound, that splitting pattern was, what was it? A quartet? It was a quartet. 3 plus 1. It was a 3 plus 1. The one above it was a 0, 0 neighbors plus 1. So it had no neighbors. All right, now if we go down to C, okay, that was our third signal. That we're just calling these A, B, and C randomly. But C was the most downfilled. It was more like the alkane around 1. So it had a standard alkane signal. It wasn't deshielded by anything because it's not near an electronegative atom. It's near more hydrocarbon chain. So we would say alkanes absorb kind of standard around 1, which it did. Now, if we look at its splitting pattern, C is next door to B. So C is split by B. And B is a CH2. So if we have 2 neighboring hydrogens, 2 plus 1 is what gave us the triplet. All right. I'm out of time, aren't I? But that is the entire problem. That's 1/4 of the assignment kind of spelled out for